Solving friction problems using Newton's second law. Suppose we have a 10 kilogram box at rest on a flat surface where the coefficients of friction are mu s equals 0.6 and mu k equals 0.4. We apply a force F horizontally on the box. What is the box's acceleration in each case? Alright, so we have F equals 50 newtons. So let's calculate static friction's maximum strength. The normal force is equal to the weight force when on a flat surface. So Fn equals the weight, which equals mass times acceleration due to gravity, 10 times 10, 100 newtons. So our frictional force for static friction is 0.6 times 100, 60 newtons. Because static friction is greater than the 50 newtons applied of the applied force, static friction will equal 50 newtons, not 60 newtons, in order to cancel out the applied force and prevent sliding from taking place. So what that means is our static friction will equal 50 newtons. Our applied force equals 50 newtons. That box is not moving because we have not yet hit the maximum static frictional force with the applied force of 50 newtons. So that happens right here where we have, here's our free body diagram, 50 newtons to the right, 50 newtons to the left, cancels out, acceleration equals 0 meters per second squared. Now let's say we have a 10 kilogram box, same box, but this time our force is 70 newtons. The applied force is 70 newtons. Since the applied force is greater than static friction's maximum, static friction is going to break and the object will slide. Kinetic friction is going to take over. So we have 0.4 times 100, 40 newtons. Now we're going to write a Newton's second law equation where the applied force is positive, same direction as acceleration, and the friction force is negative, opposite direction of acceleration. All right, so let's do Newton's second law equation for this. So we know the net force equals the stuff that makes it go minus the stuff that holds it back. Go minus back equals m times our net acceleration, which is what we're trying to solve for, that net acceleration. So the stuff that makes it go is going to be our applied force of 70 newtons. Stuff that holds it back is our 40 newton frictional force equals our mass was 10 kilograms times acceleration. So we have 30 equals 10a, and our acceleration will equal 3 meters per second squared. Don't forget your units. And go ahead and circle that. Works out nice. This means that we are speeding up, right? Because we have a positive acceleration. All right, on to another problem. Braking distance. Of course. Right. Suppose the coefficient of kinetic friction between tires and a dry roadway is 0.8. Car is initially moving at 40 meters per second, which is about 90 miles an hour, on a flat roadway and brakes hard, causing the wheels to lock or slide. How far does the car slide before it comes to rest? So this is how your brakes work, right? Your wheels are rotating, so you have this static friction happening as you're rolling. And then if you slam on the brakes and your brakes lock up, then you just start sliding and you have zero control. The way to prevent this is to pump your brakes, slamming on the brakes very rapidly. This is pretty inefficient in today's automobiles, so now most cars have anti-lock brakes. And what the anti-lock brakes do is they pump that rapidly, so if it starts to slide, it lets up, and then it allows for the tires to continue rolling without sliding. How far does a car slide before it comes to a rest? Normal force on the car is equal to its weight because the roadway is flat. The normal force and frictional force is balanced, but friction is not balanced by any force. So friction is the unbalanced force that equals mass times acceleration. So there is no stuff that makes it go in this instance. We're just going. Please don't let that confuse you. Please don't be upset that the car had to have started going somehow, so there must have been a force going way in the beginning. Remember, we don't care about how we got here. We're just dealing with a car sliding down the road, and we just want to see what's going on. So we have the net force equals the stuff that makes it go minus the stuff that holds it back equals mass times acceleration. Now, because there is no go, all we're left with is the stuff that holds it back. No. Wait. There we go. So we have our frictional force equals mass times acceleration. And what is our frictional force equal to? Well, we're sliding. So what kind of friction are we dealing with? It is kinetic friction. So that equals mu sub k times Fn. So mu sub k times Fn. I'm going to stop writing here because of the potential confusion with my bad handwriting. So that's mu sub k equals Fn, and Fn equals mg. So now we have mg on each side, or we have m on each side, excuse me, so the mass will cancel out. And what we're left with is acceleration equals mu k times g. Note the mass of the car doesn't matter. This is the acceleration of any object being brought to rest by friction. But hold on, we have not answered the question. The question's not asking for acceleration, it's asking how far does the car slide before it comes to rest. So, if A equals mu k times g, then in this case, A equals 0.8 times 10 equals 8 meters per second squared. Now, we need an equation of motion to turn my acceleration and initial velocity into a distance. The no time equation. And we get x equals 100 meters. So it's longer than a football field's length to stop. Speaking of stopping, let's stop right there.